Hi everyone, myself Dr. P. Ashok Babu. In this video, I am going to discuss about the electric potential. I am going to discuss about the what is electric potential and the electric potential for n point charges and some example on electric potential charge. So first of all, what is electric potential? To find out the electric potential or to define the electric potential, let us assume some electric field is there. Let us assume some electric field E like this. So here in electric field, I need to move a point charge from point A to point B. Let us assume 2 points, point A and point B. In electric field intensity, I want to move the charge. I want to move a point charge Q from point A to point B. To move a point charge from point A to point B, we need to apply some force or we need to do some work. So here the point charge A is located at a distance of RA from the origin and point B is located at a distance of RB from the origin. Or we can assume RA and RB are the position vectors of point A and point B from the origin. RA and RB are the position vectors of point A and point B from the origin. So here I need to I need to move the point charge from point A to point B. Here I am applying some work done against the charge or to move the point charge from point A to point B. From Coulomb's law, here the force on any charge, F is equal to Q into electric field intensity. Q is equal to electric field intensity. So that the work done in displacing the charge by an amount of dl. Therefore, we can write a formula. The work done, the differential work done, dw is equal to minus F into dl. The differential work done, dw is equal to minus F into dl. To move a point charge, here I am applying some force or I am doing some work done to move the point charge from point A to point B. Let us assume the work done is dw. dw is equal to minus F into dl, where F is the force, dl is the elemental length. Therefore, we can write dw is equal to, in place of force equal to electric field intensity into charge. Therefore, dw is equal to, we can write minus eq into dl. Minus eq into dl. So here the negative sign indicates that the work is being done by an external agent. The negative sign indicates that the work is being done by an external agent. Now I want to move the point charge. So therefore the total work done or the potential energy required, in moving a point charge Q from point A to point B in an electric field is, let us assume already we have the equation dw, the differential work done, dw is equal to, it is minus Q E into dl. If we integrate on both sides, integral of dw is equal to minus integral of Q into E into dl. Integration, differentiation cancel each other. Therefore, we have the work done is equal to minus integral, or we can keep charge outside. Therefore, minus Q into, it is E into dl. Here we are moving the point charge from point A to point B. Therefore, the work done is equal to minus Q into integral A to B E into dl. Integral the work done W is equal to minus Q into integral A to B, because we are moving the point charge from A to B. Therefore, integral A to B E into dl. So here, if you divide the equation, if you divide the work done with the charge Q, will give the potential energy per unit charge. Therefore, here I can define the potential energy per unit charges. It is VAB. VAB is equal to, it is the work done per unit charge. The work done per unit charge can be defined as potential difference. Therefore, VAB is equal to W by Q, which is equal to minus integral A to B E into dl. So this is the potential difference of a point in an electric field. Between the 2 points. So from this equation, we can observe some important points. The first one is, in determining VAB, in determining the potential difference VAB, A is the initial point and B is the final point. A is the initial point, B is the final point. Next, if VAB is negative, if VAB is negative, there is a loss in potential energy. There is a loss in potential energy in moving the point charge from A to B. If VAB is positive, VAB is positive, there is a gain in potential energy in moving the point charge from A to B. Next, third one is VAB is independent of path taken. VAB is independent of path taken. So here, if you observe the figure, so here the direction may be from A to B, or it may be from B to A. It is independent of the path taken. VAB is measured in joules per coulomb. VAB is measured in joules per coulomb. Commonly, it is referred as volts also. It can be referred as volts also. As an example, I'm assuming already we know the electric field intensity. We know that the electric field intensity E is equal to, it is Q by 4 pi epsilon naught R square into AR, where AR is a unit vector. Now, if you substitute the electric field intensity in potential equation, therefore it becomes VAB is equal to, here I am assuming minus RA to RB, where RA and RB are the position vectors of point A and point B from origin. In place of electric field intensity, here I am writing Q by 4 pi epsilon naught R square into AR. Next, if we integrate the equation, here it is Q by 4 pi epsilon naught is constant. Therefore, you can keep outside. It is integral of 1 by R square. Integral of minus integral of 1 by R square. So, integral of R square is, it is minus 1 by R. Therefore, minus of minus 1 by R, it becomes 1 by R between the limits RB to RA. Therefore, it is 1 by RB minus 1 by RA. 1 by RB minus 1 by RA. Therefore, the potential VAB becomes, VAB is equal to this Q by 4 pi epsilon naught into 1 by RB minus 1 by RA. If you separate the two potentials, here we can write VAB is equal to Q by 4 pi epsilon naught RB minus Q by 4 pi epsilon naught RA. Or we can write VAB is equal to, it is VB minus VA, where VB is equal to Q by 4 pi epsilon naught into RB, VA is equal to Q by 4 pi epsilon naught into RA. Therefore, simply we can write VAB is equal to VB minus VA. VAB is equal to, we can write VB minus VA, where VA and VB are the potential at point A and potential at point B respectively. Thus, the potential difference VAB may be recorded as the potential at B with reference to A. Potential at point B with reference to point A. Next, if we assume the potential at infinity at G is 0. If we assume the potential at infinity is 0, therefore, the potential at VA becomes 0 because it is 1 by RB, 1 by RA. If we assume the distance RA tends to infinity, therefore 1 by infinity becomes 0. Therefore, the potential at point A becomes 0. Therefore, we can modify the equation as VAB in place of VAB. Here I am directly assuming V. The potential V is equal to, the equation can be Q by 4 pi epsilon naught R. Q by 4 pi epsilon naught R. It is the general equation for potential. Therefore, we can define the potential as, the potential at any point is the potential difference between that point and a chosen point or a reference point at which the potential is 0. The potential can be defined as, the potential at any point is the potential difference between that point and a chosen point or a reference point at which the potential is 0. In another way, we can define the potential as, assuming zero potential at infinity. The potential distance R from the point charge. The potential distance from the point charge is the work done per unit charge. By an external agent in transmitting a test charge from infinity to that particular point. From infinity to that particular point. Therefore, in general, we can express the potential as V is equal to minus integral minus infinity to infinity E into dl, E into dl. So, it is a general expression in moving the point charge from infinity to that particular point, infinity to that origin or infinity to a particular point. If the point charge q in equation, in previous equation, if you assume that that point charge is located at the origin, but at a point whose position vector is r dash, in place of infinity, we are assuming the position vector as r dash. If we assume the position vector as r dash, we can write the expression for potential. We can write the expression for potential is, it is V is equal to Q by 4 pi epsilon naught into R modulus of R minus R dash. Actually, we have the equation potential V is equal to, we have Q by 4 pi epsilon naught into R. So here I am assuming 2 points. One point is, one reference point is at R and other point is at a distance of R dash. Therefore, we can find out the potential between these 2 points as V is equal to Q by 4 pi epsilon naught into modulus of R minus R dash, where modulus of R minus R dash is the distance between the two vectors. Distance between two vectors. So let us assume there are n point charges. For n point charges, let us assume Q1, Q2, so on Qn, which are located at points with position vectors R1, R2, so on Rn. Then the potential at R can be defined as, it is V of R is equal to Q1 by 4 pi epsilon naught into R minus R1 is the first charge, plus Q2 by 4 pi epsilon naught into R minus R2, plus so on Qn by 4 pi epsilon naught into modulus of R minus R1. So we can express all these charges as a summation of charges. Therefore, V of R is equal to 1 by 4 pi epsilon naught is common. We can keep outside. Then it is sigma k equal to 1 to n Qk by modulus of R minus Rk. If you want to find out any charge, let us assume k is equal to 2. Therefore, it becomes 1 by 4 pi epsilon naught into, if you substitute k equal to 2, it is Q2 by modulus of R minus R2. So, like that, we can find out the any charge. Next, this is about the potential due to point charge. So, we can find out the potential due to a continuous charge distributions like line charge, surface charge, and volume charge. If you substitute the charge Q is equal to, already we have defined the three potentials, three charges. Line charge Q is equal to this line integral rho L into dl. For surface charge, it is surface integral rho S into ds. For volume charge, volume integral rho V into dV. So we need to substitute rho L into integral rho L into dl in place of Q. For line charge, Q is equal to surface integral rho S into ds for surface charge distribution, volume integral rho V into dV for volume charge distribution. Therefore, the formula for potential is V is equal to 1 by 4 pi epsilon naught into line integral rho L dl by R minus R dash. Rho L dl by R minus R dash. Similarly, for surface charge, it is VR is equal to 1 by 4 pi epsilon naught into, it is a surface integral rho S ds by modulus of R minus R dash. Modulus of R minus R dash. For volume charge distribution, V of R equal to 1 by 4 pi epsilon naught into volume integral rho V dV by modulus of R minus R dash. R minus R dash. Next, we can relate the potential and electric field by using this equation. Here the potential V is equal to minus integral E into dl. It is a general expression for potential. General expression for potential. V is equal to, actually we have minus E into R. We can write some A to B also. R we can write RA to RB. E into dl like that. So the general expression is V is equal to minus integral E into dl plus C, where C is a constant. And the potential difference VAB can be expressed as VAB is equal to VB minus VA, which is equal to minus integral A to B E into dl, which is the potential VAB is equal to, we know that the work done per unit charge. Therefore, VAB is equal to the W by Q, which is equal to again minus integral A to B into E into dl, where E is the electric field intensity. So this is about the electric potential. Now we'll see small example on electric potential. Let us assume the 2 point charges minus 4 millicoulomb and 5 millicoulomb are located at 2, minus 1, 3, 0, 4, minus 2 respectively. So we need to find out the potential at point 1, 0, 1 by assuming zero potential at infinity. By assuming zero potential at infinity, we need to find out the potential at point 1, 0, 1. Already given Q1 is equal to minus 4 microcoulombs, QD equal to 5 microcoulombs. We have the formula V of R equal to Q1 by 4 pi epsilon naught into R minus R1 plus Q2 by 4 pi epsilon naught into R minus R2 because there are 2 point charges. The first we will find out the distance vector R minus R1, R minus R2. So here the distance vector, first distance vector R minus R1 is where R is the 1, 0, 1 and R1 is 2, minus 1, 3. So if you find out the distance between these two, it is root 6. Similarly, we will find out the distance between the 1, 0, 1, 0, 4, minus 2. So if you find out the distance between these two, it is modulus of R minus R2, which is equal to root 26. So if you substitute these two in equation, in potential equation, for V is equal to, so it is minus 4, in place of Q1, Q1 is minus 4 microcoulombs. Therefore, 10 power minus 6 keep outside, it is minus 4 by, it is 4 pi epsilon naught is also constant one, we can keep outside. It is 10 power minus 6 by 4 pi into 10 power minus 9 by 36 pi. This in place of epsilon naught into minus 4 by, it is root 6. R minus R1 is root 6 plus it is 5 coulombs by root of R minus R2 is root 26. So if you simplify the equation, we can have it is minus 5.872 kilovolts, minus 5.872 kilovolts. So in this way, we can find out the potential between n number of points also, or we can find out the potential between 10 points, 20 points, 30 points like that also. So this is a general formula is V is equal to, it is Q1 by 4 pi epsilon naught into modulus of R minus R1 plus so on. Or in a general manner, we can write V is equal to, the potential V is equal to, it is 4 pi epsilon naught into sigma K is equal to 1 to N. It is 1 by R minus R1 like that. 1 minus R minus RK. 1 minus RK. R in general, we can write QK by 1 by 4 pi epsilon naught. V is equal to 1 by 4 pi epsilon naught into sigma K is equal to 1 to N. It is QK by R minus RK. So it is a general expression to find out the potential between n number of points. So thank you everyone. Next class we'll discuss some other topic.
Like, share and subscribe. Hit the bell icon for more updates.